Hey guys, so today I'm just going to continue off where I left yesterday. So continuing on the Python Data Science Handbook. Again, the purpose of these videos is to commit into finishing this book and learn data science. But I'm going to just work on aggregations, so min, max, and everything in between this section here. And luckily, this one was or compared to yesterday, at least a lot shorter, so that's good. But yeah. This section in particular talks about the benefits of using the built-in Numpy aggregation functions when working with arrays as opposed to using the standard built-in Python functions. Because often when we're working with large amounts of data, the first thing you want to do is compute summary statistics for the data at hand. Some common stats that you want to get are the sum, the min, the max, standard deviation, mean, etc. There's a couple more that are that you could use, and I'll show you a table that's in the book later on. But anyway, let's just start with this here. So I already have this imported. So I imported NumPy as NP and imported pandas as PD. Again, the pandas is what they cover in the next section of the book, but I have some general background with pandas. This line of code here, basically I'm not going to go over it here, but it just gets the CSV file for the data I wanted to work with, and saved it under the data variable here. So in this case, I pulled up some a data set on wine from kaggle.com, and basically I worked in the wine industry, so that's why I'm just going to use this here. But anyway, and in particular, I'm going to be looking at points here. So I made an array of the points. So np.array, look at that. One of the videos came in handy here. But np.array, and then that's going to create an array, remember that. And then we want to go inside the data set, and then within that data set, we want to look at the particular column called points here, and we want to save that as the variable named points, just so that we can get this easy array to look at here. And that's only some of them, of course. There's more there in between, but yeah. So let's look at the standard function for summing this array of data here in the built-in Python. As a built-in Python function would be sum and then points. There you go. Actually, this. That will give us, hopefully, should give us the time or how long it takes to compute this line of code here. Come on. Pretty sure it worked. There we go. Just take some time there. Of a slow computer, if you couldn't tell. So we'll do the same thing here, and this one will do the MP one. I'll explain right now. So basically, what this time it does is times how long it takes to run this piece of code here, and then this piece of code, sum with points inside the parentheses here, is a built-in Python aggregation function. So it just summed this whole array and gave us the output. Or it didn't give us this because we asked for the time it took for the output. But then we did the same thing here essentially, except we used a NumPy built-in aggregation function. So the difference here would be np.sum as opposed to just the sum here. And you can see that with the NumPy one, it ran a lot quicker, as well as look at the amount of loops it did, 1,000 or 10,000 as opposed to 100. So you can see how how much more efficient NumPy ones are. You can see with min and max too. So let's do, I don't know, min. Oh, let's do. So the same thing, just so we could see there. Then np dot. Let's do min again, I guess. So we can see here did the same thing. So time it to see how long it took to run the code. And then we want the min points. So the minimum like points in that array up here. And this is using the built-in Python aggregation function. And then we did the same thing here, except we used the built-in Numpy aggregation function. You can see here with the np dot. So that's the difference there. But anyway, the Numpy one ran quicker again, so you can see that here, as well as the loops again. So yeah, you can see again how beneficial that is. So you always want to use NumPy when available, when you want to get some summary statistics for the array. Yeah, whenever you can, use NumPy basically for that type of stuff. You could even do like in this example here, I saved M as a 3x4 matrix of random values there. So that's what this does: np.random, and then gives us 3 rows and 4 columns, so 3x4, and that's what that looks like there. And then let's say we want to the max. Let's see this, the max, and then we do M. No, remember I'm learning to 0. There we go. So we could see here, like if we want to just, okay, so we named it M, right? Let me show you this first. Actually, an easier way to like simpler syntax would be that. So might be easier to, it says right here actually. Somewhere here it says oh, there it goes. I can't find it, but anyway, basically it's saying that it's, in terms of syntax, like the easiness of syntax is just easier to call the function, like sum in this case, on the object itself. So the object in our case, in this case here, is M. So we can do like M dot min. It does the same thing. But anyway, yeah, that's what I'm doing here. So when you specify the axis equals 0, so we call the max, we want the max value of this whole array, so the array M, and we specified axis equals 0. So what that does is it basically gives us the max value for each column. So 4 columns and 4 values here. So if we do M dot min and do axis equals 1, so notice we get 3 different values as opposed to 4, because when we specified axis equals 1, we want the minimum value of each row, and there's only 3 rows. And at first that was like a bit confusing, because initially I thought axis equals 0 would be like the rows, because usually axis 0 is the rows and axis 1 is the columns. But you notice how when we do axis 0 we get the columns in this case, and when we do axis 1 we get the rows. So it's like vice versa than what I initially thought it was supposed to be. But the reasoning for that is it's easier if I just pull it from here. There we go. So it says right here, the way the axis is specified here can be confusing for users coming from other languages. So the axis keyword specifies the dimension of the array that will be collapsed. So the axis we specify is gonna like tell the computer which one we want to collapse, rather than the dimension that will be returned. So specifying axis equals 0 means that the first axis will be collapsed. For 2-dimensional arrays, this means the value within each column will be aggregated. And also here's like the other aggregation functions that are available. So this whole table here. So pretty cool to check out if you want. But notice here, you got the for each one of these. You got the NAN safe version is what they call it. Basically, this is gonna go in to your array and like, let me show you here. If this 96 was a 0, not a 96, pretend it's a 0, it's gonna treat it, or sorry, not as, pretend it's an NAN, so pretend that says this. It's gonna treat every NAN as a 0, if that makes sense. Probably doesn't. Well, let's read it here. Numpy provides many other aggregation functions. Additionally, most aggregates have a NAN safe counterpart that computes the result while ignoring missing values, which are marked by the special IEEE floating point NAN value. And yeah, basically treats NAN values as 0. And that's pretty much it for this section. I mean, it finishes off with an example of average height of US presidents. If you want to check that out, I just used the wine data set instead, but they did the same thing as I did pretty much. You can see how easier it is to get things like the mean, the standard deviation, the min, and the max by calling the function on the object itself. You can see here how easier that is. And yeah, if we want to do the same thing, .std, or if you want the variance, so pretty easy to do if you want the mean even. So yeah, you can see how easier it is when you do your code like that. You get very like beneficial summary statistics for the data set you're working with. Yeah, these aggregations are some of the fundamental pieces of exploratory data analysis that will, and I guess I'll explore more of this in later chapters. But thanks.